So this one, we had been talking about tracking the concentration of H plus ions. We had been talking about the value of the equilibrium constant Kw. So this is what we were doing the last time, and we had talked about this thing, this HX thing, that any acid could be thought of as HX, and it dissociates, produces a random ion and some H and an H plus 1 ion. So acids would dissociate. We talked about strong acids, and that part was easy. That it was very easy to find the concentration of strong acids. Why? Because if you have a strong acid, the acid fully ionizes. So the concentration of the acid and the concentration of the H plus 1 ions is kind of the same. But this is not true. It's not true for weak acids. The problem with weak acids is, the problem with weak acids is that weak acids, and most organic acids are weak acids. They only ionize partially and they produce fewer H plus 1 ions. So the problem with that is, for example, ethanoic acid, it's not going to ionize fully. Like if you have 1000 molecules, only a few of them are going to ionize. So the concentration of H plus 1 over here is not going to be equal to the concentration of the acid. And which is why we're going to take the help of the equilibrium constant Kc, because that would help us in figuring out how much of the acid would actually ionize. It's the ratio of the products to reactants. So if that ratio is really high, there's a lot of products, then Kc is going to have a bigger value, and so on. So all acids, especially weak ones, they would all have this general equation, which I've written over here. And I also talked about diprotic and triprotic acid, and I told you, don't think of them as one acid. Don't think of them that H2SO4 is going to lose the H plus 1 ions in one go. Don't think that H3PO4 would lose the H plus 1 ions in one go. And instead, think of them as 2-3 different acids. For example, H2SO4 would ionize, would lose one H plus 1, and then you'll have an HSO4 minus 1 ion, and that would lose the next H plus 1 ion. So it's basically behaving as two completely separate acids. And the same was true for phosphoric acid, that it would have 3 dissociations. It wouldn't lose the 3 H plus 1 altogether. It's going to lose them one by one. So every time it becomes harder and harder, more difficult to lose H plus 1 ions. We can write that it's going to become more difficult to lose H plus 1 ions. And why does it become more difficult? As negative charge increases. TK, is this all clear? Any questions about the previous part? TK, is this fine? Lubaina, Shafak, Aruba?
Yes, sir.
Achha, so coming back to, and let me just quickly draw one line. Coming back to weak acids, I told you that weak acids are not going to ionize fully. The actual equation of a weak acid ionizing, again, you're going to have two different equations for weak acids ionizing. For example, there's ethanoic acid, and I told you it's going to ionize, right? And it would produce ethanoate ions. So frequently this equation is used. That's your HX ionizing, and that would ionize to produce A minus 1 ions and H plus 1 ions. This is what we talked about. Or you could use a different equation, which is that in reality what happens is there is no H plus 1. I did discuss this earlier as well. So what actually happens is the real equation is this one, that when ethanoic acid ionizes, the H plus 1 ions are gained by water molecules. So there's a water molecule, and that water molecule is going to gain that H plus 1 ion. So there are no H plus 1 in water. H plus 1 ions are gained by water molecules to form this thing called the hydronium ion. So that's your actual true equation. So if I write a general equation for that, that's going to be HX. HX it reacts with water and it produces a minus one ion and an H3O plus one ion. Remember, we did have a discussion on this that H plus one ions don't exist in water actually. They get absorbed by water molecules to form H3O plus one. So no matter which equation you take, eventually you get the same expression for the equilibrium constant. And this equilibrium constant is known as the dissociation constant. It's going to be the concentration of the products, which in this case would be CH3, COO minus 1 concentration divided by the concentration of the. So that's my products. And that's going to get divided by the concentration of the reactants, which in this case, it's the acid CH3, COOH. If I use the other expression, I'm still going to get the same equation. Why? Because it's going to be the product concentration, which are these two. These are my products. So CH3 COO minus 1 concentration and your H3O plus 1 concentration. The other one is and my reactants. The reactants are this one, CH3COH, and water concentrate. And I told you that water is in excess, so its concentration is a constant, so you don't write it in the expression. So no matter if you even take this expression, you're not going to write water in the expression because water is in large excess and its concentration would be constant. So this is known as your dissociation constant. So no matter if you take this equation or this equation, you get the same expression for the equilibrium constant. So that's your dissociation constant. Is this clear?
Yes,
Sir, are we adding what in the second equation?
No, we're not adding. This is I mean, it's products over reactants. I mean, this is Kc,
So,
right?
I mean, like, you wrote the equation above, right? Which is CH3COH plus H2O. So, like, are we adding water in the equation?
This is the actual true equation because I remember I previously, right at the beginning, we did discuss this that when we were ionizing water, right? I told you that water ionizes and produces these two ions, and then I told you that that's not the actual equation. The actual equation is that a water molecule is going to lose an H plus 1, and that H plus 1 would immediately get attracted to the lone pairs of another water molecule, and it would form H3O plus 1. So that's your actual true equation. Is that clear?
Okay. Yeah, it's fine.
So even in this case, what I'm suggesting is that we know that, I mean, all our lives we have studied about acids ionizing, and we talked about acids breaking down to produce these two ions, right? And again, I'm just suggesting that there is in fact no H plus 1 ions. What happens is that the H plus 1 gets attracted to the lone pairs of water molecules and it forms H3O plus 1. So whatever you call H plus 1, that's actually your H3O plus 1 ion. Okay?
All right. Yeah, I got it.
Now, the other thing is, so no matter which equation you use, you get the same expression. So the general equation for dissociation constant, that's basically your products over reactants. That if K has a large value, that means there's more dissociation. If K has a small value, that means there's lesser dissociation. Now, so I'm going to talk about the general acid equation. X minus 1 plus H plus 1. So the general equation is the K for that would be, it would be X minus 1 concentration into H plus 1 concentration divided by the HX concentration. Now, if you look at the equation, the X minus 1 concentration and the H plus 1 concentration is always the same. Like if ethanoic acid dissociates, the amount of ions are going to be produced in equal concentration, or any other acid dissociates. And for any other acid, if I write the K expression, it's going to be exactly the same. For example, for this, if I write the K expression, the products are NH3 concentration divided into H plus 1 concentration. And you're going to divide that by the NH4 plus 1 concentration. So every time products over reactants, you kind of get the same exact expression. And the quantity of these two ions would be exactly the same. The quantity of these two ions would be exactly the same. So that means X minus 1 and H plus 1, their concentration, if the acid ionizes, no matter how much it ionizes, they would be produced in equal amount. Is this point clear?
Yes, sir. Just one question.
Yes.
Why are you writing Ka? Is it not Kc?
This is Kc. Now it's an application. I mean, this is known as dissociation constant. It is Kc. I mean,
Oh,
it's just like enthalpy change, like enthalpy of formation, enthalpy of combustion. They're all enthalpy changes, right?
yeah.
So you just give them different names. Okay? So this one is known as the dissociation constant, known as Ka. A stands for acid. It's the acid dissociation constant. So the next thing is that we know that H plus 1 concentration and this other negative ion, its concentration, they are exactly the same, right? So we can instead write the formula as K is equal to H plus 1 squared. Like, why write X minus 1 in the first place? Just write H plus 1 squared and divide by Hx. Hx is our acid, so its concentration. So we get this formula, and we'll be using this formula. This would be your formula for dissociation constant, Ka. The two ions that are going to be produced in equal quantity. Okay, is this clear to everyone?
Yes, sir. So instead of writing Hx X concentration times the H concentration, we can just write H plus square, right?
Yeah, because they'll be produced in the same quantity, right?
Yeah.
I mean, so like even in the previous case, if I where did the NH3 go? Like over here, NH3 and H plus 1 would be produced in the same quantity.
So over there we can write like H plus square upon NH4 plus, right?
So I can write that as H plus 1 concentration squared divided by the NH4 plus 1 concentration. Okay, so that's going to be my acid dissociation constant. Is this clear?
Yes, sir.
And similarly, for example, H2SO4, it's going to have two different acid dissociation constants. Like it's going to be this one. There's going to be Ka for that. That's the first, let's call it Ka1, the first dissociation. So it's going to be H plus 1 concentration squared divided by the acid concentration, which is H2SO4 in this case. For the second one, it's that's going to be your second dissociation. Let's call it Ka2. It's going to be H plus 1 squared divided by the acid concentration, which in this case is HSO4 minus 1. Okay, so that's for so every dissociation, acid dissociation, is going to have a Ka value, and the Ka value is going to be a constant. It's only going to change if you change temperature. So this is known as the acid dissociation constant. And remember, it's a constant. All equilibrium constants, they only change with
Change in temperature.
yes. And usually it increases with temperature. I mean, acids are going to ionize more if you have a higher temperature because there's going to be more collision. So it increases with temperature. So that's your Ka. Now coming back to this Ka. Okay, what do we do with this Ka? So what do we do with this Ka? Now you've got three things. Now remember, all weak acids are going to have a Ka value. I mean, you can just Google these Ka values. Every weak acid, its Ka value is calculated. For example, if I Ka values of weak acids, so you have all these Ka of weak acids given. I mean, these are standard values. It's they're calculated at room temperature. So table of common Ka value. So by just looking at the Ka value, you can figure out whether it's going to be a strong acid or a weak acid. if you have a higher k value, that means there's going to be more h plus 1. There's going to be more dissociation. So that means it's going to be a stronger acid. Vice versa, if it's a lower k value, that automatically would indicate that it's going to be a lower k value would indicate that it's a weaker acid. Is this clear as well?
Yes, sir.
Yes.
Plus, remember, people don't like values that are too small or too big. They're not good for graphs. Okay, we did discuss that. For example, this is coming out to be 1.6 times 10 power minus 14. That's a very weak acid. Most of these values are kind of really small for weak acids. So the problem is, it's pretty hard to actually make a graph out of these values. I mean, the range is really, like, if somebody's going to ask you to make a graph and plot all the k values on a piece of graph paper, it would be very hard to actually plot these values. So we did discuss this as well. What do? You take log of that, right? So instead of dealing with k values, a lot of times people discuss pk values. I mean, it's much harder to actually communicate 7.9 into 10 to the power minus 5 to someone rather than just saying pk is 4.1. So again, the negative log of k values, I told you that p stands for p minus log. That's pk. Is this clear?
Yeah.
Yes, sir.
Okay, just like we don't deal with H+1 concentration, we talk about pH. And there was something wrong with pH. What was that something that was wrong? That the pH scale is completely inverted. It's like if pH is low, that means H+1 is high, and if H+1 is high, that means or H+1 is low, then that means pH is high. The same goes for pK. So if you have a stronger acid, you've got higher K values, the pK value is going to be lower. And if you have just like pH, like if you have a lower pH, that means you have more H+1. So similarly, if you have a lower pK, that means there's more Ka. So a lower Ka value means a higher pK value. Is this clear as well?
Yeah.
Okay, and I did tell you why the scale was inverted, because you're multiplying. If you multiply something with -1, the scale gets inverted. And I did explain this, that 3 and 5 is bigger, but if you take -3 and -5, then -3 is the bigger one. So the scale kind of gets inverted or upside down if you multiply any series of numbers with -1. Anyways, this one. So just remember, if you see a higher pK value, that means it's a weak acid. And if you see a very low, just like pH, if you see a very low pK value, for example, you got 1.9, that's a pretty strong acid. And we do know hydrogen sulfate ions, the pK values are kind of strong, right? So where 1.8 sulfurous acid, that's a pretty low pK value. That means it's a strong acid. Is this clear?
Yes,
The
sir.
lower the pK value, the stronger the acid.
The lower the pK value, yes. Or
Okay.
or vice versa, the higher the Ka value. Higher the Ka value, that means there's going to be more H+1 ions. The numerator is going to be bigger. More dissociation would happen. So a higher Ka value indicates a stronger acid, but if you take negative log of that, you always get a smaller value. Okay, so when it comes to pK, you always you look for the lower value, which automatically means that the K value is high. So we're going to do some questions on this. We did have, let's say we have the questions are going to be kind of simple, not that difficult. Most of the questions would be, the first type of questions are going to be very simple. And in those questions, there are three things in the equation. So I mean, there's nothing. You just have to just do calculations. Just put in values in this, plug in values. If you're given the value of K and you're given the asset concentration, you can figure out the third thing. So out of the three things, two things would be given, and you can find the third thing. That's it. So for example, let's try and do some questions. So I've got ethanoic acid, which is CH3. Its concentration is provided. And let's say the concentration is 0.5 mole per dm cube, right? And we can find the pK value or the Ka value. I think there is ethanoic acid somewhere over here. Acetic acid is ethanoic acid, I think. CH3, CH2, yep. Wait a second, acetic acid. Yes, this is ethanoic acid. The value that's given for K is 1.8 times 10 per minus 5. So we're going to take that value. So we have K for this, ethanoic acid. And that is given as 1.8. One thing I did forget is the unit of Ka. Remember, it's concentration squared divided by concentration. So the unit is mole per dm cube. Okay, that's the unit for Ka. So anyways, you have Ka. And they're asking you to find pH. So you just write the expression for K, which is that we know that K is equal to H+1 concentration. Just wait one second.